Last session, we went over topological sorts. Topological sort is a pattern that we can use to solve, several problems in like course schedule. And how we will detect when I can use topological sort, you will see the problem definition. If you have some dependencies, for example, I want to go really fast right now. Let's say we have some dependencies, A to B. We say A is prerequisite to course B. And we have also B to C. Also, we have some dependencies like this, B to D, and also, let's say C to D. We have some dependencies, and we want to know how we can run or schedule all the courses, and we shouldn't violate all of these rules because we have to have all of these dependencies. And the idea was we can create a graph based on these dependencies. For example, if we have A here, A to B, B to C, also B to D, we create a directed graph, also C to D. We create a graph, as you can see in the code we did. I put, I pasted my code here because I don't want to, spend lots of time for the previous session. As you can see here, we have a topological sort, and is number of nodes. Here is 1, 2, 3, 4 nodes we have, and edges are, A, comma B. Actually, the input is a list of pairs like this. Well, it'll be A, B, B, C. For this, simple example, and C, D. Something like that. Or they can be numbers from 0 to any value. Okay. So we have the N and edges, and this is my edges. This is my edges. And what was the first step? We wanted to build a graph with N and edges. We wrote a separate function. I strongly recommend to do that to make your top module really cleaner and shorter. We build a graph, and so we have graph and in degree. And the in degree means, every node, what is the in degree of every node? For example, A, in degree of A is 0 because it doesn't have any inputs edge. But in degree of B is 1, in degree of D is 1 because it has only 1 input edge. And in degree of D is 2 because it has 2 edges. We do all of them inside of the build graph. I don't want to go over this. You can see here. And we use 2 hash maps for graph and in degree. But the assumption is all of the, but the assumption is, the edges are some numbers, 0, 1, 2, and -1. We don't have any letters. So let's say we have N vertices, right? And all of the edges are, will be from one node to another one. So each of these numbers, the nodes will be 0, 1, 2, and -1. So that's why we do the use 2 hash maps here, and we create in degree hash map, and we say the initial value in degree of I is 0 for all of the nodes. And the graph will be for each node, we use adjacency lists. For each node, we initialize with empty lists for all the nodes. And the nodes are starting from 0 to n-1. Okay, and then we go over edges. For each edge, we create, we update the graph and also the in degree. I don't want to go over this because we did in the last session. So we create the graph and in degree. And what was the algorithm? Algorithm was, we wanted to, let me erase this. Okay, we wanted to go one by one and remove sources at each stage. For example, here in the initial state, we need to know how many sources we have. And the source is a node with in degree of 0. And now A is our sources. That's why we create a queue. Here, actually, it is a deque. Deque is a double linked list. We use a double linked list for queue. And we create a queue keep the sources inside of the queue. And we go over in degree, and whenever in degree of the, every vertex is 0, it means that it is source, and we append in this queue. And the approach we use is BFS, and you know that in BFS we use a queue. That's why we use deque from collections in Python, and you can use any, you have to know in your language which data structure is exactly equivalent to the double linked list, which is deque here. So we went over, while loop, and here we'll say, first of all, we pop the source, and we append in the output. And so if we have A, we append A in the output, and then we go over and delete this and delete all the edges. How we do this? We go over for child in graph of vertex, means all of the nodes that are connected to A, and we have only one child for A. We have B, so we have to decrease in degree of this because we popped out A. So we decrease in degree, and then we say if it is 0, it means it is my new source, and now it is 0. We will append this in the sources. In this next round, again, we will pop B, which is my new source, and we are appending in the output, which is sorted order. And then we need to update all of the children of this B in degree, right? And let's say we go over children of this, it is C and D. So C will be, this will be deleted and D will be deleted, right? And as you can see here, C will be our new source. So because in degree of child, which is C here, is 0, we will append in the source. And the next round, we will pop this guy and we will write this here. And we will update D, these in degree, and D will be the new source. And the last round, we will pop D, we will pop it, and we will add it in the output, but it doesn't have any children, so sources will be empty, while loop will be finished, and at the end, we will return sorted order. And why we checking this guy, and which if the sorted order is equal to n. If it is not equal to n, it means that we had a cycle. And if we have a cycle, we will, let's say, we have A, B, C, D, and this, like this. If you have a cycle, after I'm removing this and removing this in degree, right? We don't have any source. All of them has one in degree, right? One input edge. So this while sources will be finished, but we added only A in the output. It means that we have a cycle. That's why, based on requirements of the question, we have to return empty list, because it means that we don't have any valid topological sort. We cannot schedule courses with their given dependencies. We will return empty list, and then if it is equal, we will return the sorted order. So what is the second, today's question? Let me give you one example, and you will see why it is really important. So far it was review, and I want to go over, go and define today's problem. So let's say we have a graph like this. I want to go over, A, B, C, D, E. Okay, so I want to go have a really simple example. So I want to find the topological sort for this. The initially we have A and B as sources, right? So I have two options. In the first example, we said, okay, I can select one of them, A. I will update these guys, and the next round, B is my source. I will do B. I will remove these guys, and the next round I have C as a source. We'll have C. I will remove it, and all of these guys will be removed. And D and E, I will select one of them, D, be, and the last step will be E. But as you can see, we can have lots of topological sorts, lots of different orders. Let me back to, or let me do rewrite this. So let's go in and do this again, and you will see the question is return all orders, not only one of the orders. In the first step, I have A or B. Actually, I can have A or B, right? Because we have two sources. In the actually the previous exam, the previous problem, we simply selected the one of the sources. But right now, I can select A or B. If I select A, I have another sub-problem, and I can do topological sort for that, right? And I will add topological sort for this. Also, for B, let's say I have A, B, C, D, and E. Let's say I reselect B. We will remove this, and we need to do the topological sort for this guy, and I will have something like that. And it reminds, if you can see, whenever we had lots of problems in the previous meetups, when you see you have more than one option, it reminds us recursive algorithms, right? I don't have only one option. I can select A or B. Even we can have more. We can have n options at each step. When we have this kind of, when you are in this kind of situations, recursive approach will be the most really helpful, really easiest one. You can handle using the BFS, but I strongly recommend, if you have this kind of problems, DFS or actually recursive solutions will be the best. And we know that if we have, I want to review all the lessons we had in the previous sessions, because in this problem, we will review all of the important patterns we had so far. So far, in the basic problem, we did the BFS algorithm, right? It is the BFS algorithm. And now we want to do the recursive solution also to return all the orders. And we know that when we try different options, sometimes we need to do the backtracking. If we have data structures, because they are automatically passed and in Python by reference, in other languages, it is strongly recommended to pass data structures by reference. It means that we don't have copy of that data structure. We have only one instance of that data structure. That's why when for example, when I remove A and I update all of my data structures and call this the sub-problem, the topological sort sub-problem for the remaining graph, I'm updating some of the data structures when I'm going inside, like in degree and sources, I update all of them, right? But when I want to try the same sub-problem, if I select B, I have to reverse or backtrack all of the changes I did for sources and in degree, which are the really important data structures. We use them in this sub-problem. So that's why I'm saying this problem is really important, and it is really one of the really hard problems in for coding interviews, because you need to know you need to be really fluent in using the queue to implement the base of the topological sort. You need to know how you write recursive solutions for this guy, and also the backtracking. Now, based on these explanations, I want to go and in the first step, I want to convert this BFS algorithm to DFS algorithm. And in the first step, I want to only return one of the orders. Even if we have multiple answers, we want to return only one of them. It means that I want to directly, exactly convert this guy to recursive. And it is really another good lesson. That's how we can convert a BFS directly to a DFS or recursive algorithm without thinking, without overthinking about the problem, okay? And then we will convert that recursive problem to return all orders. We will have two steps. Any questions so far? If any comment or question, I'm really happy to answer. Okay, we don't.
Yeah, is there any reason why the double-ended queue was used instead of the list? I just curious.
Yeah, sure. I will explain. Good question. Actually, right now, if you see, for this problem, we only append at the end, right? We append, and we don't have any remove, right? For this basic question, the base topological sort, as you can see, we always append at the end of sources, and also we pop from the beginning of that, right? We need a data structure with with a time complexity of order of 1 to add and remove from the beginning of the data structure and also the end of the data structure. We don't want to cost for appending and removing from our data structure any time complexity. Okay, so the base data structure is double linked list, because in double linked list, if you want to add in, append in the first of the linked lists or at the end of this, it will be done with order of constant, which is order of 1. And also, if you want to remove from the beginning or and from the end, it will be done with the order of constant. That's why if you use deque or double linked list, it guarantees that all of your operations won't cost you for order of more than order of 1. Mm-hmm. Any question? I can hear some noise.
I have a question. So,
Sure.
yeah, instead of doubly ended queue, you could use just regular queue also, right?
Yes. Let's say, we have, actually regular queue, when we say regular queue, okay? So regular queue means we want to add from the beginning, right? We want to add at the end and pop from the beginning, right?
Yeah.
This is so if, let's say, we want to, the queue, so when we talk about queue is a general term, right? You have to see how it is implemented in any language.
Yeah.
Okay, so queue means, I want to add at the end. So let's say we have a linked list, a single linked list. Inserting at the end of linked lists, single linked list, will be done with the order of n, because in single linked list we have only head pointer, right? We have only head pointer. We have to traverse whole linked list to be able to add at the end. Okay, so it means that single linked list is not the good, data structure to me. When we talk about queue, it is definitely double linked list, because in queue we want to add at the end and pop from the beginning, and both of them should be done in order of 1. Okay, but if you go, let's say, simple array inserting at the end is done with order of 1, but removing from the beginning is done with order of n, because if we remove from the array, simple array of vector, all of the cells should be shifted 1 unit to the left. And it means that removing from the beginning will be done with the order of n. So that's why simple array is not our, optimal data structure here. single linked list is not optimal data structure here. And that's why we go over double linked list. But if you use double linked list or deque, it will, it will guarantee that you don't cost more for the basic operations, removing and adding. Okay, go ahead.
Just to add a note here, popping from the beginning of a list, like the regular list that we use in Python, we can specify if we want to pop, like we can specify the index value as 0. That is O1 operation.
No, if it is list, it is not O1.
I think I have like read it somewhere in the documentation. Like, I don't know if they're using circular array to maintain that, or how.
See, basic list, simple list, you can remove this, but it costs order of n, right? But maybe in some libraries you can find that they implemented that operation. But if you want to be sure that you are doing the you want to be sure, I strongly recommend to use double linked list and deque. But I'm sure that for regular list, if you remove from the beginning, it will cost order of n.
I think in Python, the list and the deque is the same time of complexity for Python.
No. Actually, when we talk about lists, it is kind of
like the bracket. I mean, in Python.
Yeah.
And then the dot end, right? Then you have the dot pop instead of the dot pop left. I think the time complexity is the same.
But dot pop is popping from end of the list, right?
Dot pop will pop from
0. You have to write pop 0, right?
No, it's just dot pop. Okay, I see. Actually, how do you? I mean, to implement the stack in Python, you just do the dot pop, right? It's from the end of the list.
In order to let's say we have a list and we want to implement a stack, right? Okay, we want to add. Let's go do this some basic questions. Okay, so what is this stack? We insert at the end of this, right? And we pop from the end of this. So if you use a simple list, right, append at the end, and whenever you want to pop from the end, it will be a stack, right?
Yeah.
And you can use simple list, a basic list, to implement your stack. But for queue, we cannot, because in queue, adding at the end, if you use the simple, removing from the beginning is not done with order of constant. But if you saw,
for the queue, maybe we just use a deque for Python, and for stack we just use a list. Right?
Yes,
you're
exactly.
right. Yeah, thank you.
Yeah, exactly. Actually, also you can use deque for a stack. It doesn't. It's not wrong. Let's say you have deque, right, and you want to implement a stack. You have to append at the end, but you have to pop also from in. You shouldn't write pop left. You should write pop. That's it. Okay, but for stack, even simple lists will work because it doesn't cost you more than order of constants. Okay, does it make sense?
Yeah, thank you.
You're welcome. But one of you guys said that in lists, the removing from the beginning is done with order of constant. As far as I know, we don't have this, but every day we have some updates.
Yeah, I think you're right. I might have got confused in the beginning, so yeah, it's not constant.
Yeah. Actually, I talked about all of these guys, in the previous meetups, but because so we have new members, new attendees. That's why I'm not talking about it, because always I talked about all of the data structures we are using, and but the best one is double linked lists, because you don't worry about, are not worried about any extra costs. Okay. Okay, perfect. Let's go and convert this part, which is our BFS algorithm, Oh, let me, sorry, I need to mute all you guys, but whenever you have, you ask, you have a question, you can unmute yourself. Yeah, beautiful, thank you. I think it will be much more, better. We can manage the session better. Okay, so let's go and in the first step, convert this code, this part actually, I'm talking about this part, which is our BFS algorithm. And we want to convert this to recursive. I don't want to write a code. I already wrote this. I want to show this and talk this because I want to go over this part that we want to do, return all orders. And let me raise all of these guys. I wrote already the code and I will explain over it. And it is really a good lesson that how we can convert any BFS algorithm to recursive. So as you can see here, we do some operations inside the while loop, right? We are, iterative operations. So what's happening in the recursive calls? In recursive calls also we do, we call same operations for several times. It means that the inside of this while loop will be the body of my recursive function. And instead of while sources, because we don't want to write while inside of recursive, I will write if sources. It means that if we have any source, okay? And that, at the end, after we do all of these parts, we will call same recursive function to redo all of these operations. This is the logic. I mean that there is no difference between iterative and recursive. The only implementation, the logic is exactly same as each other. I will put all of these guys as the body of my recursive call. And instead of while sources, I will write if sources. And at the end, I will call same function with the updated data structures, because we are updating sorted order, we are updating in degree, and we are updating sources. I will call same function with updated data structures, updated inputs, and that's it. Let me bring my code for this guy, because I think because the main focus of today's session is to find all orders. That's why I wrote the code before, because the logic is exactly like the BFS one. So let's go and see what's going on here. So as you can see, let me move this a little top to have exactly line by line corresponding. It will be helpful. Okay. So we have same top level topological sorts, and as you can see, all of these guys is exactly same as each other. We have build graph, we have sources. Okay, we have all of them. But instead of doing the BFS, we want to do the recursive calls. I will write topological sort recursive. So how can I do the topological sort? How can I calculate? I need graph. I need sources. I need in degree, and also sorted order, because I will put all of my answer inside of the sorted order. That's it. Instead of doing this, the main part is to detect which variables, which data structures you need to calculate the topological sorts. And because if you remember, if we don't have any topological sorts, or if we have a cycle, we should return empty list. That's why inside of this, I'm returning true or false. I will say if it is true, return sorted order. And the sorted order is my output, but we pass as inputs. And it is really easy to control when we pass our outputs as inputs. And I return true or false to say we have any order or not. Okay, say if we have return sorted order, I'm assuming I calculated inside of this function, the sorted order. If, but if it is true, return it. If it's not, return empty list. So now it's time to do the recursive function. As you can see, while sources, all of these guys are exactly same here. I didn't change anything, only I changed while to if, right? Instead of while, we will use if, because we do the while by recursive calls. And then I will call this guy with the updated data structures. As you can see, this topological sort is inside of if statement. Because if we don't have any source, so what we do here, when the sources are finished, we do this if statement, right? We do same operations here. If we don't have any source, it means while loop is finished, and here it means that we are done. So I will check if len of sorted order is not, so right now, because I'm returning true or false, I'm saying if it is equal to len of in degree, which is n, I didn't pass n here. I could pass n also here, but you know, it is extra because the length of in degree is, or length of even graph is number of nodes, number of vertices. If I say if these guys are equal, go ahead and return true. And sorted order is updated inside of this because we are appending here, okay? And when I'm calling here, I can simply return sorted order. But the thing that's the basic thing that you have to know if you are, you know, you just started, you are, you know, you are not really fluent in coding or data structure, is that when we pass all of these guys as a data structure, all of them are data structure. This is hash map, this is hash map, this is a list, and this is a also list, right? Actually, this is a queue, sorry. This is a deque, hash map, and this is a hash map also. We talked about this here, you know, right? In degree is hash map and graph is hash map. All of them are data structure. It means that every change I do inside of these recursive calls can be seen outside of the, can be seen in the caller function, the function who is calling this function, right? So that's why sorted order will be our answer, and we can return this. Any question about this part? Because this is really the base of this next step that we want to try all of the sources. I talked about it, right? Here we say if sources, go ahead and pop one of the sources and go ahead, right? But in the next step, we will say, okay, I want to return all of the orders. I should try all sources, not only one of them. If I have, you know, 3 sources in a specific step, I have to do all of these operations in a for loop because I have to try all options, okay? And you will see in the next step how we are doing the backtracking. And this is the best problem in my experience, in my teaching experience, the base problem to teach how backtracking is working, because we will have, you know, really interesting discussions why we are doing the backtracking. And I really love this problem. I mean, you know, the returning the all orders. But in order to solve it, you have to know how to write the recursive. We can handle also in the BFS, but it is a little complicated. That's why I prefer to go over recursive solution. When we have different options, it is much more easier to use recursive approach. Any question about converting the BFS to DFS? Go ahead.
I got a question, not about converting, but so in this case, we don't need backtracking, right?
No, backtracking, you know, right now, every time we have only one recursive call, right?
Mm-hmm.
Each recursive call, you know, inside of this function, we have only one recursive call. We know we don't need backtracking. Backtracking is needed when we have more than recursive call inside of the recursive function. Okay?
Right, okay.
When we have one, we don't need. But when we have several recursive calls inside of a function, we do some changes and call the function, the recursive call, in the next call, we have to revert all the changes because we don't want to have the previous changes impact in the next call.
Okay.
Okay. And you will see, you know, this is really a perfect example to learn, you know, backtracking forever. Whenever I teach this problem for anyone, after that they say, okay, I know backtracking, it is really clear to me, and you will see in the next step. But I want to be sure that everyone also converting the BFS to DFS in this way, exactly copy and paste. You don't need to do, even I could handle this part like exactly like this, but I prefer to return true also, because in some questions they say return true or false. Can you schedule, you know, these course? You have to return true or false. And in this code, we return true or false also if the order. We do this, both of them in one function.
For the DFS approach for this new problem, do we need to have the in degree, or can we also use a visiting flag?
Okay. So, you know, you mean you need another, you know, data structure for visited.
Yeah,
No,
instead
right?
of an in degree, we don't use the in degree, we use a visited.
Actually, we need in degree to detect sources, right? This is part of our logic, right? So because in here, you know, as you can see, we need in degree to detect what is the new sources, right? Why we don't use visited array? Because sources actually is working like, you know, visited for us, because based on sources, all the nodes we need to pop, we put in sources. And whenever sources is done, we are done. It is acting like visited data structure we use in the other questions.
I see, thank you.
Okay, you know, it is like here, yeah, okay, perfect. Any question for this part? And I want to go over, talk about how we can convert this, because right now, this is exactly, let me write something here. So this question, you know, this question is, you know, recursive. Actually, the naming is recursive, right? Recursive solution to return one order. Now we're going to go and convert this guy to have more, you know, to have all orders. If you don't have any question, I can go to the next part. But please, you know, review this part, converting a BFS to DFS. It is really helpful. You know, you can see that recursive is nothing than, you know, the iterative. Instead of while, you have if. And then, you know, in here, actually, we go and call again we run all of this part of code, and you call this and run all of these guys. And instead of while, you have if, and that's it. That's why, you know, I'm saying a BFS and DFS are exactly the same. And we don't do any, you know, the logic is the same. Okay, let's go and convert this guy to, I'm gonna go over here. Okay, so I don't want to change top level. We have all of these guys. We need to build the graph. We need to find the sources. But here, I will have some changes here. I will do some, you know, changes, you know, and then I will write the code. Okay, so I need another. First of all, we should detect that. Do we need any other inputs for this recursive call or not? Right now, it does all of these guys, and it returns only one of the sorted orders, right? So I need another input, which is all orders for results, right? So that's why I can write here. Let me write in the red color, I need to define all answers, which is empty. And I will add as one of the other inputs here, all answers. And I'm assuming inside of this recursive call, the topological sort recursive, it will update all answers. And then I will return all of these answers, right? And then, you know, I can, let's say I want to do this. I don't need if, because we return, you know, we update all answers. So I also, though I don't need to return this guy, I don't need to return this. I simply, after I'm calling this guy, I will return all answers. And this is the top level change, okay? First of all, we have to figure out that. I saw lots of people put this as return output of the return part of the function, but it is really easier, especially in Python, to put even your outputs as inputs, your return values as the input of your function. So initially it is empty. We pass this to the recursive call, and we are assuming that it will update all answers, and we will return it. But the main part is updating this function. As I said, you know, let's say here I will do, you know, we have another input, all answers. Well, let me talk about it, and then I will go and, you know, update, write the code in the IDE, and you will see it will be much more cleaner and easy to read. So if we have source, instead of doing this guy, if you have any sources, instead of doing all of these guys, for only one of the vertices, we have to do for all of the sources, right? I need to change this guy. I need to change all of these guys, right? So instead of doing this guy, I will write for, because we wanna do the same operation for all sources, okay? I will write for vertex, we'll say, you know, I will write for vertex in sources, right? For vertex in sources, go ahead and do all of these operations. Well, let's say I want to do all of these guys here. Let's say I want to do and call all of them. Will it be correct or not? So let's say I'm doing the only for loop over this, and I'm calling all of these guys, right? And at the end, instead of this guy, I will say if this is equal. I shouldn't return true, right? I have to, if I'm here, it means that I found one order, right? I found one order. I will write all answers. Actually, you know, instead of this return true, let me change this guy. Instead of this guy, we'll write all answers that append sorted order. This is the basic parts without, you know, there are lots of points. I want to go step by step. So instead of doing all of these operations, finding, you know, I want to pop one of the sources and call same function, you know, find this topological sort for the remaining of the graph, right? But we say, instead of doing this, you have to do for all of the sources. Do for all of them. And at the end, if we have, you know, the length of sorted order is equal to this, if the sources is empty, go ahead and append the sorted order in all answers. This is the structure of our code. But as I said before, if we change where, you know, let's say we are changing sorted order, we are changing in degree, we are changing sources, and inside of the for loop, we call our recursive call. In the next round, we are changing all of these guys, right? Sorted order, in degree, and sources. In the next round, we don't want to have all of the changes for the next vertex. Do you remember we said A, B, C, D, E. If I remove this guy, let's say A, the 4 vertex in sources, we have sources right now initially has 2 items, right? If I remove this, pop this, and at the end, I will update all of these guys. I will call my recursive call here. In the next round, if I remove this, I will have this graph to call this. If I don't revert all the changes, I have to revert. What is my objective in the for loop? In the first step, I want to remove this. I will call the same function for this remaining graph. In the next round of loop here, in the for loop, I want to remove B. But I need to have A and C and D and E. So actually, this is also E. I need to call this. So it means that before popping this guy, I need to revert all of the thing I've done in the first round. That's why I'm saying in recursive calls, when you have more than recursive call inside of the function, you need to do backtracking. It means that we need to do backtracking for all of the inputs we have here. The graph, actually we don't change graph. As you can see, graph is read-only. We use graph only to read some values. We don't change it. But sources is changing. In degree is changing and sorted is changing. And all of them are data structures. It means that they are they passed by reference. So I need to revert all of them. So that's the important part of this problem. Any question so far? If you don't have, I wanna go to my IDE and write the code based on these explanations.
I had a question.
Sure.
So if we would just copy them, of course, for the time it just takes a whole lot longer. I think it gets slower, but would that also work? Would that remove the backtracking need?
Yes, exactly. Yeah, exactly. This is, really a good point. This is the easiest way to bypass backtracking, right? Let's say I want to do some changes, all of these guys. I can make a copy from these guys and change over the copy. I can do all the changes over the copy and pass to the recursive call. This is one of the solutions. I recommend for some of my students to do this in the interviews because it is better than getting confused. So if we can copy, definitely it is your solution will be correct. But copying has time complexity because when we want to copy all of these guys, actually we have order of n for each copy, right? We have extra cost. Also, we have extra space. So that's why backtracking is, really important. But in terms of interview, if you are, you can do first by copying, you will copy, let's say, I'm copying here sources.copy, and I can make this, put this in, sources copy, in degree copies, and then I will do all of changes in the copy. And I will pass the copies to this guy. And then next round, I have original one, right? Again, I will copy them and I will do changes. I'm actually bypassing the backtracking, difficulties, okay? But you do this first and then say, okay, I can improve this by backtracking, and go ahead and do some of the data structures. Some changes are easy to backtrack, but some of them are really difficult. For example, here, sources, as you can see, what changes we do for sources. Actually, for sources, as you can see, for in degree, we do, increase, or, we have decreasing of any one item, one of the children. So we can simply revert it by increasing by one. And also sorted order, we simply append a vertex, so we can remove it. We append at the end, and we can remove it simply after recursive call, right? But for sources, we do pop left, and then we append, and we have some conditions to appending a child, right? We can do backtracking, but it doesn't, in some cases, we prefer like this for sources to make a copy of this, because doing the backtracking, you have to do lots of logic to detect which changes you did, right? Actually we popped left, and then I have to, keep it, which item I popped. And then here we append some children's, right? Children. And it is really difficult to detect what I did over sources and to do the reverts. So that's why the best decision for this problem is to make a copy of sources to bypass backtracking for that, because the logic we are doing for sources is not that easy. We have to do lots of backtracking. In the backtracking part, we have to do for loop to detect what we did before and revert it. But for sorted order, we can do simply backtracking, and also for the in degree, because for in degree we just decrease by one. We can simply revert it, and that's it. So it means that I need to do some backtracking after this recursive call, right? And let's go and I wanna, for this session, actually, I wanna go use my also keyboard to write the code, to have a cleaner code here. Okay, right now we know how we can, let me check my, okay, what we want to do, right? We know that we need to do the backtracking for these guys. But for sources, we want to make a copy of sources, because it will cost a lot to do the reverting for sources. But for sorted order and in degree, we do the backtracking. And that's why I'm saying this problem is really comprehensive problem to see how we are playing with backtracking. It's better to do backtracking and when it's not. And also, as I think Nico was talking about, is that, we can bypass it by copying all of the data structures. Let me, I don't know. Okay, yeah. Actually, I put, here, this is the recursive code. I want to convert this to return all orders. And we talked about it right now, right? And we have here all of these guys, but I said I need to, let's do all of these guys here. Because we want to return all orders, I want to write, all answers. All answers will be empty, and I will pass this to all answers to the input. And I don't need actually the if statement, because here we calculate all of the all of the orders, and I will return all answers. Okay. So this is the first change. I talked about it, in the OneNote. You call this, and I don't know why it is returning this. I have lots of space here. Okay. We put all answers and returns. And here I need to add this guy here as all answers. It is weird. I have a space. Okay. And also don't forget to add, because we changed the signature of our function, right? I have to do this first. But instead of doing the if inside of the if statements, we do only one operation here. I will do the for loop. I said you have to go for vertex in sources. I wanna do all of these operations inside of this guy. So I need a tab to have all of these guys, right? So, but before doing this, we talked about it. Sources, we need to make a copy of this because it is a little complicated to revert all the operations we do over the sources. So that's why I wanna copy of, make a copy of this. So let's go and do this here. So I want to make a copy. In order to make a copy, I will write, so sources, what is the type of source? It is deque, right? It is deque. In order to make a copy of that, we have to make a deque of that. In Python, you know, we write it like this. Let's say sources copy will be equal to deque of sources. Actually, we are casting sources to deque. It means we are copying this guy. So we did the copy, and then we have to do all the operations over sources over the sources that copy. Sources copy. Does it make sense? Any questions so far? You know, actually we made a, you know, we made it this guy, and then we do the sources. Instead of this, I'll be writing sources of copy.popleft. I don't want to change the sources. And I will add vertex inside of the sorted order, because it is, you know, we have to append the vertex which we popped from the sources copy to the sorted order, right? And in the next step, we do the for child inside it. I don't need to change these parts. In degree of childless, and we change all of these. But you know, we shouldn't use sources. As I said, we use sources copy instead of sources. And in the recursive calls, we have in degree, because we didn't copy in degree, same data structure, sorted order, but sources we changed it, and we want to pass sources copy. Okay, we want to pass sources copy here. Okay, as you can see, we bypassed backtracking for sources by making a copy of that, and I redid all operations. But we have to revert. Let's say, you know, this part is backtracking part. Backtracking for backtracking of in degree. And what is the next? It is sorted order. Every input that are in the data structure, we have to backtrack, because for the next vertex we wanna, which is source, we wanna pop it and do with the original graph. We don't want to have the previous changes impact in the next one. So what we did for sorted order, we append something, so we can remove it. sorted order that remove what vertex. We can remove it. We reverted this. And for this part, for in degree, we have some if statements, right? And I have to check for all of the children of the vertex, right? For all of the children of the vertex, we decrease by 1. So I need a for loop to increase for all of the children of the vertex, their in degree value. So I need a for loop for child in graph vertex. All of the children of the vertex that we already decrease, I need to increase. In degree of child will be plus equal to 1. So that's it. So we made a, and the reason we make a copy, because we have lots of logic here to see which values we appended, and because it is Q, the order of the sources is really important to us. It is really challenging to handle and to revert all of the changes we did. That's why we simply handle this by copying this guy. And sources, we have the original sources. We copy this and we apply all the changes and call over recursive call. But for vertex, for sorted order and in degree, as you can see, we can simply revert it. And what we have to do at the end, we'll say if it is equal, I have one of the answers, right? This was for the previous question. I will, actually we are not returning anything in this function. As you can see here, let me check. When you call our recursive call, we just updating all answers. So we don't return any valid value. So that's why I will write here all answers that append sorted order. And if it is not equal to len of in degree, we shouldn't change it because it is a cycle, okay? If we go all different paths, and some of them will be a cycle, and so we don't have, if we have cycle, whenever we reach here, we'll see we don't append and all answers will be empty. But if it is equal to n, it means that we have a valid topological sort order and we can add it in the answers. And that's it. Let me copy and paste this in the OneNote. I don't need to copy build graph because it is same for all the questions. Okay, but I think it is really okay. Let me paste this here. Text mode. Okay, this, I don't know, but it is keeping to, I'm gonna do this here. It is really weird. Okay, let me change the location. So this is, the finding the all answers for our question. And let me make this, it is really tiny, I think, let me like this one. And I will have to a little rearrange it. It's okay. So we have right now, our solution for finding all topological sort orders. As you can see, we call this here, and we add one all answers. We add it here. Instead of doing only for one of these guys, we can do a for loop, and we update all of our data structures. We call, also here also we updating this guy. We call this, and at the end, which is really important parts, we are backtracking. And at the end, if source is empty, we will go outside of this if statement. We will check if this is equal to in degree, len of in degrees, which is the number of nodes we can append this. And as you can see, exactly, we did backtracking for this guy. Let me switch to my pen. Okay, as you can see here, let me use my pen. We use here the sorted order, and we have backtracking for this guy. And for this part, we do the backtracking in this part, right? And we don't need to do backtracking for sources because we handle the backtracking by copying. And the reason we do this, it is really reasonable because source is a queue, and in the queue, the order is really important. And also, we do some logic here. We don't know how many sources are appended inside of this if statement. We can handle this actually. You can, do this as a practice, as a homework. But we copy this. Actually, I want to show you. We have 3 candidates: sources, in degree, and sorted order, to do the backtracking. And as you can see, we do for 2 of them, which are easier, the backtracking. With one of them, which is sources, we do not. We just handle by copying. And all answers doesn't need any backtracking because it is a global variable. It should be, the change of this should be should impact all of the recursive calls, because its scope is global, but all of these guys are local scope, right? That's why we need to backtrack. You have to, and also we don't need to do anything for graph because it is read-only. It is constant. We are not changing this. So this is the strategy. You have to check which of all of these inputs are passed by reference, and most and usually data structures are passed by reference. And in order to bypass all the change inside of this recursive call, we have to reverse all the changes, because we have different recursive calls inside of the recursive call. I'm trying to teach the reason and philosophy that we need to do backtracking. If you have one recursive call, definitely you don't need to do backtracking. But if you have more than one, you need backtracking if you have some local scope variables which are passed by reference. If they are passed by value, when we pass by value, it means that we make a copy. We make a copy of them. But when we say by passing by reference, we don't make a copy. We have one instance of all of these guys. That's why we need to do backtracking or make a copy, as we did here for sources. And all answers scope is general, is global. We don't need to do this. Any question for this solution? If you have any question, I know this is really one of the really hard problems, and usually in the interviews interviewers don't dive into this problem directly. They ask you the topological sorts, and then they say, okay, go ahead and extend this. And if you know, as you can see, if you are fluent in backtracking and recursive, it is not that difficult. But they are not asking, first that, go ahead and write an algorithm to return all topological sorts. No, it's definitely they ask you first write a function to return one of them, and then say, okay, how we can return all of them. Okay, any question, any comments so far? Let me check here the chat part. Yeah, there is a question that are the previous meetups recorded? Yes, it is. And please go to this link. This is my YouTube channel, and you can see I posted I uploaded all of the recorded meetups, and also I will add more videos on this meetups and some educational some other educational videos. And yeah, if you also subscribe, you will see you will be notified of new videos. So let's go, and if you don't have any question, I hope everyone is understood this. What's the how we handled a really difficult problem in an easy way, but you have to review to see to observe, to digest all of these material, all of these contents. Okay, so what is the time complexity of this? We didn't talk about time complexity of this problem. Any comment, any suggestion? Usually finding the time complexity for recursive solutions is really difficult if you want to go based on your code. One hint is to think about general solution, general problem. It is kind of solving a probability problem, a statistical problem. We have n vertices, and we want to find all topological sorts. In the worst case, how many topological sorts we can have? Let's say we don't have any dependency. Let's say we have n vertices, and we don't have any dependency. How many topological orders we will have? So let's say we have 1, 2, 3, let's say 0, 4, and 5. We have 6 nodes, and we don't have any dependencies. Let's say edges is empty. This is the worst case, right? Because if we have any dependency, it will decrease the number of orders, right? Topological sorts. The worst case is when we don't have any dependency. How many topological sorts we will have? It is a math question, right?
N factorial?
N factorial, yes. Because for the first, let's say for the first location, I need n, I have n options, right? And if I select this for the second place, I need n minus 1 because I selected one of them. This is like, finding all the count of, the permutations, right? And finally, we have 1. It will be n factorial, right? And here, let's say, yeah, the n is the number of nodes, vertices. Or in this example, it is number of courses, number of events. So the worst case, and when we are talking about time complexity, we are talking about worst case, right? So this is n factorial. So it means that we do n factorial times, we will, this recursive call will be called n factorial times. So what we are doing inside of this guy, we are handling, actually we already calculated in, this for loop. We already calculated the n factorial for this. But as you can see, in this for loop, we do extra operations, or even here. What is the, for every of these n factorial, we do 2 for loops. What is the order of this for loop? And these two guys. What is the first one?
N.
Graph of vertex, right? Graph of vertex is the number of edges of one node, right? What will be the maximum number of edges for each node?
N minus 1.
N minus 1. Let's say we have a complete graph. Let's say we use E. In the graph problems, we use V and E as number of vertices and E number of edges. So this will be E, right? At most will be E, number of edges. Also here, we will have E, right? Also, we do some copying here. The deque, we do copying. And this is the sources, and the order of this will be V. Because in the worst case, we will have V sources, V nodes, right? And let's say all of them are, sources. I'm going really step by step, how to calculate this. But usually we say number of edges in the, but you have to discuss with the interviewer with assumption that number of edges is greater than number of vertices. We can write here for all of these n factorial, actually n also I want to use V as the number of vertices. So for V factorial, for each of them I have V plus E plus E. What will be the V plus E plus E? We can say V plus E times V plus E, but in most cases we say, because we are assuming the number of edges are more than number of, the vertices, we can even write, V factorial times E. But, more accurate is this guy, V plus E. So let me erase all of the others. So as you can see, for recursive calls, recursive functions, you have to find the worst case. It is just, solving a, statistical problem, a probability problem. And usually we do this some permutation, like, calculations. We have V factorial, topological sort orders, but for each of them, we do some extra operations here, as you can see. Copying will be cost in the worst case V, but actually it is not V. If we have all of them source, right? Let's say all of the nodes are sources. It will be done in the one step, right? It will be done in only much more, faster, right? But in order to be more accurate, let's say we have V here, E here, E here. It will be V plus E times V factorial. And this will be time complexity. And what will be the space complexity? Actually, because we have, for a space complexity also, we have V factorial for the output, right? For our, the all answers. We need this guy. So we have same V factorial for our all answers. And for each of these guys, we use V plus E for, storing all of the information for that. We need in degree. Actually, in degree is same. We don't make a copy of this, right? But we copy the sources also for all of them. but actually if we write v factorial times v, it is kind of v factorial, right? We don't need to do that. But we have v factorial, and every of the answers, what is the length of each sorted order? It is number of edges, right? So that's why it is better to write, here, v factorial times e will be the space complexity. Because I'm also actually counting the space we required for all answers. What is the worst case for how many answers we have v factorial? And what is the length of them? It is e, the number of edges. In the worst case, we will have number of edges. And we can say that this is v factorial times e. Any comment or any question? Let me check this. So if you don't have any question, I will go over
one question.
Yeah,
is it
sure.
the number of vertices or is it number of nodes?
Which one? V?
At the end, for all answers, is the worst case for the length? Is not length of the nodes, number of nodes?
V, actually, v factorial, v is number of nodes, right? And e is number of edges, right? And we calculated, and let me, maybe I get
vertices are the nodes. Okay, sorry, I was not sure about the word.
Yeah. Actually, this is v minus 1. Actually, I get, I changed the naming of the number of nodes. That's why, maybe this source of confusion. Okay. Any comment, any question? But actually, I'm saying, in most interviews, they don't ask you, directly, they don't dive into this problem. I saw lots of people, they are asked to write, the basic topological sorts, and they say, okay, we want to extend this to return all of them, and only you talk about the solution. So you don't have enough time, and you say, okay, I can do a recursive solution, and I will do the backtracking. I will try all of the vertices. And in most cases, if you do the first part really fluent and really, with high self-confidence, and they say, okay, it's done, and let's go, and that round of interview will be finished. And this is, the scenario in most interviews. But if you do the first part really, with the struggling, it will be, my objective, my purpose, that's, of explaining this stuff is that you don't have to write this code in most scenarios. That's my point. In most cases, you talk about, this part. But usually they start with a medium problem and they extend it to the hard problem. I'm talking about top tier companies like Google, Amazon, Facebook, Apple, okay? And if you do the first part really perfect, and here only you will talk about it, you will talk about the solution, and usually they ignore it. They say, okay, you don't need to implement it, okay? Don't worry about, really difficult problems, but you need to, exercise them, practice. In the interviews, you will have, your standards will be higher than the interview threshold, and you will get the offers from these companies. Okay. And now I want to go to the sliding window pattern, which is maybe can be a little kind of resting for you guys after doing this really hard problem. And I think that would be so. Okay, I will share, this guy also for in the photos of the meetup page, and you can have access to this one, to all of these notes.